Okay, hello and welcome back. Today we're going to be exploring a very important concept when it comes to the world of limits and derivatives. Specifically, we're going to be talking about indeterminants and L'Hopital. Yes, that is how we pronounce that word right there. It's named after someone, and we're going to explore a rule called L'Hopital's rule. So get excited, here we go. So we're going to shift our perspective back to limits. We've been focusing on integrals for quite a bit. Today we're going to look at limits. So sometimes when evaluating limits, we would get a nasty fraction as our result if we were to do like a direct substitution. Sometimes we would get 0 over 0 or infinity over infinity. And when we first learned about limits, the way we would handle this is by factoring the limit, taking the numerator and denominator, factoring them, and try to cancel something, and then plugging in our value again. That's fine. But sometimes we can't factor the limit. For example, in this limit right here, we can't really factor anything meaningful out of the numerator to cancel with anything in the denominator. And we can see if we were to plug 0 into our fraction right here, we would get e to the 2 times 0 minus 1 divided by 0, which is equal to, well, e to the 2 times 0 is 0, so e to the 0 is 1. So this would be 1 minus 1 over 0, which is 0 over 0. So what will we conclude in this case? We wouldn't have been able to conclude anything previously. So we have to learn a way to tackle these kinds of limits. And that's where L'Hopital's rule comes in. There's a little like caret symbol over the O, but putting that in text is not always the easiest thing. When I was learning calculus, we used to call it like going to the hospital whenever you had to use L'Hopital's rule, because L'Hopital kind of looks like hospital. Anyways, so L'Hopital's rule says that let f and g be functions that are differentiable on some open interval containing c, except possibly at c. So c is going to be the value that our variable approaches in our limit. And then we're going to assume that g prime of x does not equal 0. That we can worry about in just a moment. The idea is if the limit of f of x over g of x as x approaches c produces an indeterminate of the form 0 over 0 or infinity over infinity, which are both bad cases, then this rule states that the limit as x approaches c of that quotient is equal to the limit as x approaches c of the derivative of the numerator divided by the derivative of the denominator, provided that the limit of the derivative exists. And this g prime of x not equaling 0, now you can see why it has to not equal 0, because if this were to equal 0, we would run into issues again. A good thing to note is L'Hopital's rule also applies to one-sided limits, and you can keep on using L'Hopital's rule. So what I mean by that is if this limit approaches 0 over 0, and you use L'Hopital's rule to get this, and again you get 0 over 0 or infinity over infinity, you can use L'Hopital's rule again on that to get a new limit. This is really, really cool, because when we prior had an integral that we couldn't solve, 0 over 0 or infinity over infinity, all we have to do is take the derivative of the numerator and take the derivative of the denominator and get a new limit. Notice how we're taking the derivative of each counterpart individually and independently. We are not taking the derivative of this fraction. If we were, then we would see the quotient rule being put into place here. But we're simply taking the derivative of the numerator and of the denominator. It's that easy. Let's see an example. So the example is the one that we saw 2 slides prior, where we're looking at the limit as x approaches 0 of that, and we saw that with direct substitution we get 0 over 0. So in order to evaluate this, we will use L'Hopital's rule. So L'Hopital's rule says that the limit as x approaches 0 of this, since it equals 0 divided by 0 with direct substitution, that will be equal to the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. So the derivative of the numerator is, well, the derivative of e to the 2x by chain rule or whatever rule it is equal to 2e to the 2x. Derivative of negative 1 is 0. And the derivative of x in the denominator is simply just 1. we have this new limit, which equals this limit by L'Hopital's rule. Now we can use direct substitution to get 2e to the 0, which is equal to 2. Therefore, this limit we started with is equal to 2. How cool is that? Such a simple rule, but it's so powerful. It's very exciting. So since it's quite simple, there aren't too many tips and tricks, but I'll give a couple just to maybe help out. So if the form of the limit that you obtain is 0 over 0 or plus or minus infinity divided by plus or minus infinity, just use L'Hopital's rule as normal. However, there are some other indeterminate forms you can get. 1 to the infinity, 0 to the 0, or infinity to the 0 are all indeterminate forms. They're undefined, unknown values. And in this case, L'Hopital's rule does not apply because there's not necessarily a quotient being involved and it doesn't equal 0 divided by 0 or infinity over infinity. So for these kinds of limits, we're going to take the natural log of both sides, compute the limit, and then e both sides. Which might sound a little bit confusing, but we'll see an example of it. The idea is to get rid of one of these exponents here or something like that, simplify the function a little bit, take the limit as x approaches whatever of that simplified function, and then e it to cancel back the original natural log that we did. Let's do some examples of L'Hopital's and also of this second case where we use a natural log. So the first question is asking us to evaluate the limit x approaches negative infinity of x squared over e to the negative x. We can try using direct substitution here, and let's see what we get. So using direct substitution, we get, well, we have negative infinity squared on the numerator, and then e to the negative infinity. So negative infinity squared is basically just infinity, and in the denominator, e to the negative infinity is e to the infinity, and e to the infinity is simply just going to be infinity. So we have an infinity over infinity, which means we should use L'Hopital's rule. Okay, so we'll start by saying using L'Hopital's rule. I always like to start out my solutions by citing that I'm using L'Hopital's rule. Otherwise, it may be a bit confusing in the math why I'm suddenly taking the derivative of the numerator and denominator. Here, I'm citing what I'm doing so it's clear to the reader and or grader why I'm doing what I'm doing. So L'Hopital's rule says that this limit is going to equal the limit as x approaches negative infinity of the numerator, the derivative of the numerator, divided by the derivative of the denominator. Okay, so we can maintain our limit as x approaches negative infinity. The derivative of the numerator is the derivative of x squared, which is simply just 2x. And the derivative of e to the negative x in the denominator is going to be negative e to the negative x. We can try using direct substitution here to evaluate this new limit. And we get, let's see, in the numerator we get 2 times negative infinity, and in the denominator we get negative e to the negative infinity, and we can see that this is going to be of some sort of like infinity over infinity thing. So that's not good either, which means we can use L'Hopital again. So we'll say, using L'Hopital's rule again, we get that the limit as x approaches negative infinity of now we're dealing with 2x over negative e to the negative x is going to be equal to the limit as x approaches negative infinity of the derivative of the numerator divided by the derivative of the denominator. And that will be equal to, well, the derivative of the numerator is the derivative of 2x, which is 2, and the derivative of negative e to the negative x is e to the negative x. And now we can try again doing direct substitution. I'll just call it ds to simplify it. Now we get 2 in the numerator, e to the negative infinity, which we can rewrite as 2 over e to the infinity. E to the infinity is a really large number, so we're dividing 2 divided by essentially infinity, which is going to be equal to 0. And there you go. That's our answer. So we started with this limit. We concluded, hey, we can't solve that normally. We're going to have to use L'Hopital's rule. So we said that this limit is equal to this limit here, but the second limit is also not great for us. We have to use L'Hopital's rule again. And we concluded this limit is equal to this limit. So these three circled limits are all equivalent to each other, and this last one was the easiest to solve. That's how we got our answer. Since all three were equal to each other, we can conclude that the limit we started with is equal to 0 as well. So there you go, that's your first example using L'Hopital's rule. Hopefully you can see how exciting of a method this is because it's so simple. Let's do another example. The limit as x approaches infinity of e to the negative x times the square root of x. We're going to start by rewriting this limit, and this is something that you should try to get used to because, as you see, these limits can produce some indeterminate values, and sometimes you have to manipulate them to get the indeterminate value that you want. So we can rewrite this as the limit as x approaches infinity of the square root of x divided by e to the x. Right, and the reason I did that is if we do direct substitution on the original limit, we get e to the negative infinity times the square root of infinity, and from there it's not immediately obvious that it's an indeterminate form. We can rearrange this a little bit now to see that, okay, this will be square root of infinity divided by e to the infinity, which is basically the same thing that we just did. And then you'll get to the conclusion that we're about to make. But sometimes it's nice to just rearrange it from the beginning. So now let's see if we use direct substitution on this new limit, which is equivalent to the old limit. We get the square root of infinity divided by e to the infinity. Square root of infinity is just, infinity, and the denominator is also infinity, so it looks like we're going to have to use L'Hopital's rule. So using L'Hopital's rule, we can conclude that the limit that we started with, x approaches infinity of e to the negative x times the square root of x, well, we'll rewrite it the way that we like to write it, which is the square root of x, which I'm going to write as x to the 1/2, divided by e to the x. That will be equal to the limit as x approaches infinity of d dx of the numerator divided by d dx of the denominator. And now we can compute these derivatives on their own. The derivative of x to the 1/2 power is 1/2 x to the negative 1/2 power, and the derivative of e to the x is e to the x. We can rewrite this again now since I'm not a big fan of negative exponents. So this is the limit as x approaches infinity of 1 over 2e to the x times the square root of x. And now we can try using direct substitution again. And we get 1 divided by 2 times e to the infinity times the square root of infinity. The denominator is going to be an absolutely massive number. We're doing 1 divided by that absolutely massive number, and that will approach 0. So this equals 0. And that's our answer. So another example using L'Hopital's rule, key thing here is to not be afraid to rearrange what you're taking the limit of to get a form that suits you for you to use L'Hopital's rule. And now let's do this example. The limit as x approaches infinity of 1 plus 1 over x to the x. So again, we should try using direct substitution to see if we can get any insight as to what the answer is. So this will be 1 plus 1 over infinity to the infinity. 1 over infinity is 0, so this is 1 plus 0 to the infinity, which is 1 to the infinity. If we scroll back a little bit, we see that 1 to the infinity is an indeterminate form, which may be a little bit surprising to some people. Like, why would this be indeterminate? I really encourage you to research this and see why it's the case. It's quite interesting to learn about, and you may see the example that we're doing in the explanation for it. But indeed, this is indeterminate. So my tip says that you take the natural log, compute the limit, then e both sides. Okay, so what do we mean by that? Let's say that we set y, let's let y equal 1 plus 1 over x to the x. Then we want to compute the limit as x approaches infinity of y. Okay, that's fine. But how about we take the natural log of both sides as the tips suggested? So that means the ln of y is going to be equal to the natural log of the right-hand side. And this is where knowing your natural logarithm properties will come in handy a lot. Because the reason we take the natural log of both sides is mainly because of this nasty exponent here. That's what was causing the infinity exponent in our direct substitution answer. So a property of natural logarithms is if we have ln of a to the b, that's equal to b ln of a. So we're going to use that property to our advantage. So on the left-hand side, we still have ln of y. And on the right-hand side, we can rewrite this as x times the natural logarithm of 1 plus 1 over x. Okay, so now let's consider if we took, hypothetically, the limit as x approaches infinity of the natural logarithm of y. Remember, we were looking for the limit as x approaches infinity of just y. And let's say that that is equal to a. Then, if we were to e both sides, meaning we do e to the power of that side, we get e to the limit as x approaches infinity of ln of y is equal to e to the a. The left-hand side becomes the limit as x approaches infinity of e to the ln of y, which we're saying is equal to e to the a. The e's and the ln's cancel, so we get the limit as x approaches infinity of y, and we'll say that that will equal e to the a. And this is what we're targeting. So essentially what we did is we said, hey, the limit as x approaches infinity of y, which is what we started with, is too difficult for us to calculate. So let's consider a modified version of the limit, which is of this form. Hopefully this will be easier to compute the limit of. We'll call that a. And if we know this limit, we can perform some alchemy to get this limit that we were looking for, namely by following this procedure here, which is just to compute e to the a. That's all we need to do. So that's what we're doing. That's the game plan. I'll move this off to the side. We've computed the natural log of y. Now let's consider computing the limit as x approaches infinity of ln of y, which is equal to the limit as x approaches infinity of x times the natural log of 1 plus 1 over x. Okay, so let's try using direct substitution. So using direct substitution, we get infinity times the natural log of 1 plus 1 over infinity. 1 over infinity is basically 0, so we're left with the natural log of 1 inside the parentheses. ln of 1 is equal to 0, and actually this is also not a great form to deal with, infinity times 0. So we can't really work with this. This does not necessarily equal 0 nor infinity. So that's not good. And so maybe you're like, okay, how do we solve this now? We can't use L'Hopital's rule because it's not 0 over 0, it's not infinity over infinity. And we probably can't take the natural log of both sides because we already did, and then we would have an ln of y on one side, which would be kind of nasty. But also there's no exponent on this other side to deal with. So what do? This is where the creativity of messing around with your limit will come in handy. We can rewrite this limit as the limit as x approaches infinity of ln of 1 plus 1 over x, and that other x factor, I'm going to divide it by 1 over x. Division by 1 over x is the same thing as multiplying by x. And now if we were to use direct substitution, we get ln of 1 plus 1 over infinity, which we said was 1, divided by 1 over infinity. The natural log of 1 is 0. 1 over infinity is 0. Aha! Now we can use L'Hopital's rule. So, you have to be getting used to this, where maybe you use direct substitution and you get like infinity times 0, and then just do a little bit of rearrangement and you can see, I've gotten the form that I want, 0 over 0. I can work with this. Okay, hi, so I wanted to briefly come in here and explain why infinity times 0 is an indeterminate or a bad form. I kind of just brushed over it in the video, but I realized that it probably deserves more explanation, and indeed it is a bad form. But why? It wasn't one of the ones listed earlier on in the video. We saw 0 over 0, infinity over infinity, 1 to the infinity, etc., but not infinity times 0. So the way we can think about this is we have infinity times 0. Let's leave the 0 as it is. And let's think about infinity. How can we possibly obtain infinity just using normal algebra functions or whatever? Okay, so let's just say we have a fraction, and the numerator, let's just say it's 1. If we make the denominator really, really small, we're going to obtain a large number. And as we make it smaller and smaller, we get a larger and larger number, and we'll assume that we're staying with positive denominators. And in fact, if you take the limit as x approaches 0 of 1 over x, you get infinity. So, with that in mind, we can rethink about our infinity factor as this 1 over a really, really tiny amount, which is essentially 0 because the limit as x approaches 0 of 1 over x, that equals infinity. So let's just say that infinity is like it's 1 over 0. Then you have 0 times infinity is 0 times 1 over 0, which is 0 over 0. The math is a little bit sketchy, I'll admit, but this is one way of thinking of, infinity times 0 is equal to 0 over 0. You can similarly show that it's equal to infinity over infinity, so that means you should use L'Hopital's rule. So all of this to say is that if you get an indeterminate form that you don't know, think about how you can transform it into something that is familiar to you. In this case, we transform it into 0 over 0, which indicates that we should use L'Hopital's rule. If we just saw infinity times 0, we wouldn't have known to use L'Hopital's rule. So take a moment to transform it into something that is familiar to you, and once you see that it is 0 over 0, then you'll know I have to use L'Hopital's rule, so I need to change my limit such that it's a fraction that is equal to 0 over 0 or something along those lines. So that's how we made that transformation. That's what you should be thinking. I hope that helps. Let's continue with the video. So now we'll use L'Hopital's rule. So using L'Hopital, we can conclude that the limit as x approaches infinity of ln of 1 plus 1 over x divided by 1 over x is equal to the limit as x approaches infinity of the derivative of the numerator divided by the derivative of the denominator. Okay, so the derivative of the numerator, ln of 1 plus 1 over x, that's going to be equal to 1 over 1 plus 1 over x times the derivative of the inside. So the derivative of 1 is 0, the derivative of 1 over x is equal to the derivative of x to the negative 1 power. And if you take that derivative using the power rule, you get negative 1 over x squared. And in the denominator, we're taking the derivative of 1 over x again, which we just said is negative 1 over x squared. And remember, this is equal to the limit as x approaches infinity. I always forget that. We can see that these two terms cancel. So they cancel. So this is equal to the limit as x approaches infinity of 1 over 1 plus 1 over x. And now we can use direct substitution again to get 1 over 1 plus 1 over infinity, which is equal to 1. So all of that to say is the limit as x approaches infinity of the natural log of y is equal to 1. So we've done this first step up here. We calculated a equals 1. Now we'll take the e of both sides, and we see that when we do that, the left-hand side becomes the limit that we were targeting, since y equals this expression, and this is the thing we started with, and that's equal to e to the a, so a was 1. So this means the limit as x approaches infinity of 1 plus 1 over x to the x is equal to e to the 1, or simply just e. In practice, you would want to show these steps using the values that were obtained here, but since I was running out of space and since I already explained this, I didn't really do it. But there you go. This is your example of taking the natural logarithm of both sides. As you can see, there's a lot of manipulation that has to be done within the limits and when doing the natural log and things like that. So start to become comfortable with that. Review your natural log properties and you'll be in good shape. So that concludes our short video on L'Hopital's rule. Really important trick, really powerful. Hope you enjoyed. Hope you learned something. As always, take care.